Hello, my name is Mads Barnkop from Kaiser Power Electronics, and this is part 2 of the Huawei Remote Radio Unit 3908 teardown, and this is the circuit analysis of this teardown. So here I have a overview of the whole amplifier unit itself. Over here in the yellow marked area is the whole power supply unit. I'm not going to concentrate on that and explain anything about that other than the two large silvered squares are DC-DC converters, and that we have the input power at the top and the filtered DC voltages at the bottom. Then I will go on with the green squared area, which is the central processing unit area that handles all the network data and the packaging and depackaging of the telecom protocols. Then I will move on to the receiving part, which takes a look at the analog pathways and into the analog to digital conversion. And at last we will look at the transmit part, which takes the digital signal and converts it into an analog signal for the power amplifier and the Diplexer unit, which will round this circuit analysis off. So let's get on with the central processing units. The central processing unit area consists of a whole wide range of CPUs, RAM and FPGAs, and some designated digital signal processing CPUs. Now the first things that we have is down here in the right corner. We have the optical input-output connectors. There are two 10 gigabit optical connectors. These are controlled by a PMC Quad-Phi 10 gigabit controller. This controller is among one of the few things actually controlled by this CPU down here, which is a Freescale PowerQuick 2 CPU. It's a 200 MHz CPU with 2 times 256 megabytes of DDR2 RAM from Hynix that sits here to the right. Maybe my head is blocking for it right now. Among this, there is 3 Altera Cyclone 3 FPGAs. Now these are custom programmed units, so it's hard to say which FPGA does what job, but it is for sure that this one over here sits nearest the analog part, and the two others sits nearest to the transmitting part. There is also 2 different Texas Instruments of a very famous old series of DSP chips, which is the TMS320. They are, however, quite different, as the one sitting up here in the right corner is a fixed point DSP, which means that it can only calculate integers, while the other 1 GHz chip we have over here in the left side can calculate with floating point numbers. So let's move on to the receiving part. The receiving part of the board is what I have cut out here. It consists of actually 2 parts, as the signal comes in over here on the left side, goes on and is split out into 2 lanes. There's one for the 3G network here, and then there is another one for the 4G network over here. But I will now zoom in at the start over here, and we will take a closer look at the signal path. So here we have the 2 out of phase signals that comes in from the input of the Diplexer, and the first thing that we meet is a SHIB 73021, which is a down conversion mixer for 3G networks. Now this down conversion mixer is most likely getting its local oscillator frequency from the ADF 4110 oscillator that sits over here to the right. Now from here the 2 signals goes on through some filtering, and there is a CPAD SAW filter. SAW filters are sonic acoustic wave filters, and I have a demonstration and explanation of how SAW filters work in another video, and you can find a link for that in the description. Now from here on the signal keeps moving up through these two paths, and from here we will have to track the signal through the ground stitching, and we end up over here at the two variable gain amplifiers. Now these two are the intermediate step before entering either the 3G or 4G region of this board. So if we move on with the 3G part, the signal goes down here into these two lanes. As you can see, these are some quite long strings of inductors and capacitors, and then there come a little range of resistors. And then down here we have a 14-bit 150 megasamples per second chip, which is the 806654. And this is a analog to digital conversion IC that is primarily made for 3G and 2G networks. From here on, the data stream is handed over to one of the Altera Cyclone 3 FPGAs and is packaged back into the telecom protocol. Now if we go back up here to the variable gain amplifiers, and we follow the second track out to the 4G part, there is some interesting small ICs starting with MCL, and I think these are used to actually multiplex the two-phased signals into a single data line, and this is all clocked by this 809516, which is a 14 output clock generator, which also has a local or a voltage controlled oscillator that goes up to 2 GHz. So this is both used for down conversion mixing and highly likely also for these small SPDT switches. Now this signal is then fed into a Maxim 2039E, which is a down conversion mixer, as it is implemented in this circuit. Now as you can see, there's actually two of these, and I'm not quite sure if it continues with two lanes, but it might get over here and then get recombined with another switch, because there is only one last analog to digital conversion chip. So these two out of phase signals are most likely timed and treated in each their down conversion mixer before they are fed down through this analog line here to the 809230, which is a 11-bit but 200 megasamples per second ADC chip. And this is the 4G data stream conversion, but the 4G telecom protocol is first packaged in one of the Altera Cyclone 3 CPUs. So let's move on to the transmitting part. Here at the transmitting part of the board, there is actually two identical lines, so I have only marked up ICs at one of them, and we will only look at one of them. So over here is one of the circuits, and over here is the other. So this is the one we will take a look at. I did not mark up the local oscillator and clock generator. This is the same IC as mentioned in the last part of the receiving part that we just saw. This is the 809516, which was a 14 output clock generator and also had a up to 2 GHz voltage controlled oscillator built in. This is used for the up conversion of the signal. I also have another video where I explain up conversion and down conversion a little more in detail, and I will also put a link to that in the description. So let's zoom in and start on this signal path analysis. Now we first start off with the two 809788 digital to analog converter chips. These are 16-bit, 800 megasamples per second ICs. Now these get their digital data stream from one of the Altera Cyclone 3 FPGAs, and then converted into 2 out-of-phase analog streams, which goes up here through the ground stitching and hits a ADL 5375, which is a upconversion modulator, and it works in the range of 400 MHz to 6 GHz. From here on, the analog signal goes up through a ceramic resonator bandpass filter. I also explained this a little more in detail in another video, and you can find the link in the description. From here on, the filtered analog signal continues to through 2 transistors. And if this is used to cut off or even modulate it, I'm not quite sure, because it actually breaks the line completely. And the you can see here it's not really used because there's not solder in any components in over here, so this jump point is not used in this configuration. But up here is 2 HPJ2F, which are hybrid couplers, which can conduct 45 watts of RF power. Now with the setup here with the 4 transistors, this can actually switch the phasing of the signal, so this is all timing the whole phase of the signal that gets sent to the transmitter and power amplifier. The first amplifier that we meet is this little Freescale, which is the M004N, which is a high linearity amplifier. This amplifier is 17 dB from a 2.2 GHz signal. Now the last thing before entering the power amplifier is a little digital step attenuator. This goes from 0 to 31.5 dB in 0.5 dB steps, and it is serial controlled interfaced with a 6-bit control number, and the signal strength can then be controlled simply here before entering the power amplifier itself. So let's move on to the power amplifier. The power amplifier also consists of 2 paths. So here we have one at the left side and one at the right side, which are identical. Now we can see up here that the outputs had been broken off when I took the amplifier apart the wrong way to start with. So let's zoom in on this golden madness and take a closer look at the signal paths. We'll start down here at the SMA connector. So we have the input from the transmitting mainboard here, and we can easily follow these RF paths in a power amplifier because they are heavily insulated from any other grounding plane or ground stitching. The first amplifier chip is a Infineon PTMA 1840, which is a 40 watt RF LD MOS amplifier. We can also notice this the huge ceramic capacitors that then gets smaller and smaller as we get closer to the chip itself, and also the path for the power supply is all quarter or half wave length signal path to cancel out any switching noise from the power supply itself. From here on out, we can see the output lane here goes up through a Singer 2 hybrid coupler, which is a 90-degree phase coupler, and the 2 outputs gives us 2 out-of-phase signals that enter each their power amplifier transistor, which here is the NXP BLF6G20 LS140 RF LD MOS transistor, able of conducting 140 watts of RF power. Now the soldering here is not quite as nice as seen in some other units, but it could also be much worse. If we look at the signal path length, they are quite even here on the input side. And up here we can also notice the whole power supply line here. Large capacitors get lesser and smaller. Also the quarter wavelength paths to avoid any switching noise issues. Now if we look at the output signal path, we can see it goes up here to another hybrid coupler and also goes up here to the same hybrid coupler. Now these signal path lengths are about the same, so this is most likely not a Dorothy amplifier setup, but maybe just a regular push-pull or maybe intermediate amplifier. Now from the hybrid coupler, the signal goes out to the circulator. I've explained this in some previous videos, but this circulator is quite easy to explain. It relies on a magnetic principle where current can only conduct one way in a magnetic field. So any signal that comes into port 1 will come out at port 2, and any signal that comes back from the antenna and comes into port 2 will go to port 3, which is then terminated by a 50 ohm Anaran termination resistor here. And as there is no signal or energy left here, as it's all shunted to ground, there's zero energy going from 3 to 1. But it is completely impossible for any signal to come back from the antenna, from port 2 to port 1 and back into the power amplifier. This is the whole job of a circulator. Now here on the output there's some interesting details on how capacitive coupling works in a radio frequency environment. This little SMA connector is for diagnostics or a supervision output. And as we can see, we have these sawtooth or comb-like fins, and this is basically just capacitively coupled to the main signal line, and like this it can actually read out a good strength signal. At last, here we have the Diplexer taken apart. The lid is off, and let's just start by zooming in. If we start down at the antenna connectors, we have down here at the bottom, we can also see there are some circuit boards sitting on top here, and we have 4 outputs. These are all diagnostics or raw antenna outputs that can be used for other purposes than actually connecting to the Taylor network. Now as we get up here, we can see that the small metal cylinders here are all the transmitting cavities, and the large one all sits in the receiving part. Now there is, for me this is all radio frequency black boxing and black magic and such, because the amount of engineering and calculations that has to go into setting this thing up and actually getting it machined into specs, and then have all these tuned cavities in the Diplexer to have it work to split out the frequencies and such. It's quite amazing. It's really a nice piece of machined hardware. And over here at the lid we can see the pins with some are rounded and some are just screws and threaded pins. That goes into these metal cylinders to actually tune the cavity to the exact frequency that is needed at that part of the Diplexer. But this is really one of the best looking Diplexers that I have seen in a long while. No doubt about that. So overall, how does this Huawei base station compare to the Sony, the Ericsson, or the what was it, Nokia Siemens Networks amplifiers? Well, if I had gotten all 3 marks without any designated chip names on them and so on, I would not have been able to tell the difference. But knowing that this is a 4G amplifier, where some of the others also are, but it's like this amplifier unit uses slightly older ICs and components, and it does not contain any special made ICs as have been seen in the other brands. So it seems like Huawei relies completely on using FPGAs and no custom ICs. Or maybe they're actually just using a more open design, which makes it more scalable to be used along with other base stations. This is all guesswork, of course, but thank you for watching this circuit analysis, and I hope you enjoyed both part 1, the teardown, and then this part 2 of the circuit walkthroughs. So, until next time, see ya.